Good morning, good afternoon, and good evening to all our viewers. Welcome to the Productivity Talks by the Asian Productivity Organization. I'm Gözde Bosnalı from APO Secretariat and today's moderator. APO is an international organization committed to improving productivity in the Asia-Pacific region. And APO Productivity Talks are a platform where the innovative ideas for productivity enhancement are addressed by experts, practitioners, and academicians. Before we start, I would like to thank our viewers for following us, and to be informed about the upcoming P Talks, please subscribe to our channel. You can leave your comments and questions in the chat box, and we will answer them after the session. Innovation-led and green productivity is amongst the main focus areas for APO. So today's very interesting P-Talk topic will be on climate actions in the Asian agricultural sector. For more sustainable farming practices and higher agricultural productivity with reduced greenhouse gas emissions, the introduction and replication of climate-friendly agricultural practices and smart technologies are significant. In today's P-Talk, our guest speaker will be Dr. Toshihiro Hasegawa, executive scientist from Japanese National Agriculture and Food Research Organization, NARO. NARO is also the host for the new APO Center of Excellence on Climate Smart Agriculture, established this year in March. Dr. Hasegawa will highlight the climate actions needed in Asian agriculture, drawing from the latest report by the Intergovernmental Panel on Climate Change. He will also introduce innovative approaches developed by NARO to mitigate the effects of climate change in the agricultural sector in Asia. Welcome, Dr. Hasegawa. It's a pleasure to have you with us today.
Hello, good morning, good afternoon, good evening, wherever you are. I'm very happy to be here and thank you for sharing this opportunity with us. Thank you.
Yeah, thank you for accepting our invitation. So before we start, Dr. Hasegawa, let me share a little of your background with our viewers. Dr. Hasegawa completed his PhD in agriculture at Kyoto University in Japan with a thesis on modeling the effect of nitrogen on rice growth and development. He worked as an academician in Kyushu Tokai and Hokkaido universities in Japan and served in the National Institute for Agro-Environmental Sciences as a senior researcher, group leader, manager, and executive scientist, mainly excelling on climate change adaptation. Dr. Hasegawa also won various awards with his research projects on the impacts of climate change on rice and paddy ecosystem from prestigious institutes in Japan. So, Dr. Hasegawa, I also have the honor of working with you on APO Centers of Excellence program. Me and our viewers are very enthusiastic to learn more about today's topic from you. You may please start your presentation.
Thank you very much for a nice introduction. Let me start my slide, this topic. Before I forget, I would like to thank two of the co-authors here who provided the nice slides. I'm representing this climate actions in the Asian agriculture sector, and not just on my own, but on behalf of all NARO in studying this climate change actions. And Dr. Shirato and Dr. Ono have provided these slides, some of the slides. Okay, let me move on to the topic. And what I'm going to introduce today is just mainly three things. One, why climate actions? I think it seems obvious, but let me show you some of the information that obtained from the latest climate report from IPCC, followed by a few narrow research activities. Not all, but some key research findings that we've obtained for climate change mitigation action and some of the climate information service that may be supporting some of the climate actions. And finally, we would like to conclude. And let me start from climate action, why climate action is needed. And based on this IPCC report, IPCC, as you know, is the Intergovernmental Panel on Climate Change, established in about 30 some years. Uh, and then assessing the sciences related to climate change periodically. It started in 1990 in first round, and second round is going to 1995. And now current is almost the end of the sixth assessment cycle, started in 2014 and finishes just July 2023. And there are three groups separately working, or separately but collaboratively working on the collecting, assessing the new scientific findings. First group is working on the physical science, how climate is going to change, and the climate change. The second group is now looks at the impacts of climate change and adaptation, how we can cope with that climate change. Third group is about how we can mitigate climate change and reduce the greenhouse gas emission. And lastly, these are synthesized, are put into the synthesized report in early this year. This is the finding, a major message from Working Group 1 showing the already global warming is taking place. On your left-hand slide, and this is this on your x-axis, and that's showing the year from the early century, about for the past 2,000 years. And on your y-axis is the temperature rise from the pre-industrial period between 1850 to 1900. As you can see, this sharp increase starting around this pre-industrial timeline, and currently it's already 1.90 degree warmer than the pre-industrial time. And the important message from Working Group 1 is this increase is mainly, or almost all, is from the human-induced climate change. The human activity using the fossil fuel is causing this high increase of the temperature. What are the causes of the increases in temperature of 1.9 degree? So the different types of greenhouse gases are emitted in the atmosphere, but major ones on your right-hand side are two. One is the famous carbon dioxide, and that's contributing to about 80 or 70% of the global warming currently taking place. But at the same time, methane is another potent greenhouse gas, and that's also contributing to this large increase in current temperature. It's about 0.5 degree contribution is made by methane emission. What about the future? There are different scenarios prepared by IPCC. One that has this very low emission, trying to cut greenhouse gas emission as soon as possible, very radically, whereas SSP 585 is the one with very high emissions. And one bad news from this IPCC report is that no matter how you change the scenario of climate change, greenhouse gas emission, best estimates of warming isn't that much difference in the near term, 2020 to 2040. It's almost inevitable to see the 1.5 degree warming world in the near future. But from the midterm to the end century, we see a huge differences in global warming depending on how you use fossil fuel. If you make radical changes, we can keep the global warming at this 1.5 or 1.4 levels to the end of the century, whereas we keep on using the fossil fuel, and we see some of the higher global warming above even 3 degrees. So that's quite alarming. What does the future climate look like in Asia? Projected climate change in Asia, and on the top panel, and that's about 1.5 degree world, whereas the lower panels that's showing 4 degree warming. On your left-hand side, there's a temperature rise, and in the middle two are precipitation. And here on your right hand is maximum temperature over 35, very high temperature affecting many sectors. And as you can see, there's a very high changes in almost everywhere under high global warming scenarios. But you see also the precipitation-wise, very contrasting effects can take place in the different regions. Some blue, greenish ones is heavier precipitation, whereas the lighter color shows drier conditions. So the regional discrepancies will become even larger. That creates a huge uncertain future of the precipitation events. And we have our projection of the risks associated with these changes are quite alarming as well. We have different kinds of, this is so-called burning amber. As temperature goes up from the pre-industrial level, what the risk will be like is showing in this figure. And risks are projected higher and severer as the temperature rises. And particularly some of the systems very unique, for instance, coral reefs and high mountain biodiversity is really easily affected. 1.9 degree is the current warming level. It's already been affected in very high, at really high risk. In RFC2, the extreme weather is already taking place, and it's going to get worse even when 1.5 degree warming. RFC3 is the distribution of impacts, and some of the impacts are already showing at this current stage, but it's getting worse above 2 degree. And even larger scale impacts will be affected, projected to be worse and even 2 degree and higher scenarios. Importantly, these risk level transitions are projected to be occurring at a lower global warming level than the previous reports. So we just published this working reports from Working Group 2 on climate change impacts and adaptation, and just last year. And this is the 6th cycle, and this is a really big short summary of what's new and the 6th assessment report. Compared to the last report, we've seen lots more impacts reported in the range of different sectors, regions, and some of the impacts are apparently from anthropogenic climate change. Human-induced climate change are affecting our society and ecosystems. And disasters are already affecting food, water, and health, and compounded by many other factors, and resulting in cascading risks. And these risks are disproportionately affecting different people, particularly on the marginal people. And we also assess impacts below 1.5 degree or above 5.5 degree. And this 1.5 degree is the key threshold temperature. And again, risk levels will be higher at the lower warming level than previously reported. Good news is adaptation is already ongoing, but bad news is that that's not sufficient. As I was involved in this food chapter, on chapter number 5, particularly looking at agriculture and food systems related to climate change. And one important message from our report is that human-induced climate change has already slowed the agricultural growth in many different parts of the world, but in very different ways depending on regions. And on your left top panel showing the maize impacts rice on your left-hand side, soybean and wheat. These are the full panels showing the negative impacts with the red signs, and these anthropogenic impacts occurring from 1980s to current 2010 is already had a negative impact of crop productivity in many species. And the impacts or causes of these strains constraints are different and diverse and can be somehow compounding. And we already see some of the negative impacts. This is an example from rice, and negative impacts are shown in some Asian countries caused by ozone, and also pests, and aridity or dryness, and heat. And unfortunately, many of the multiple of constraints are occurring in Asia, Southeast Asia, and also South Asia. So that we need to overcome some of these negative impacts from different factors and in the future as well. And we look at the future, more heat exposure is projected. Water scarcity is getting harder in some regions, particularly the mountainous region, which relies on heavily on snowmelt. And at 2 degrees of warming, and snowmelt could experience 20% decline in water availability for agriculture after 2050. And climate change will negatively impact food security, particularly above 2 degrees. More places get food insecure above 2 degrees. Flooding risks will become harder, particularly in low-lying areas where many people live, and also many agriculture is practiced particularly in Asia. So these effects are not just on crops in human, but also compounding that will be affecting crop yields, and productivity effect is also undermined by lower labor productivity, and that results in reduced house income and raising soared food prices. And it started from the local effects and is now spreading. It will proceed into the potentially global effects. So these compounding effects are very hard to project, but it's likely to happen at events that are caused by climate extreme and hazards. So what are the adaptation options we see in this? We are now that's already taking place. Some are already reported to be effective. Cultivar improvements for droughts and heat-tolerant varieties. Agroforestry that uses the multiple crops grown at the same time. And diversification is one of the keywords that reduces negative impacts and also convey multiple benefits. Community-based adaptation is really important in terms of to reduce the inequity and the food crisis issues. Biodiversity in town will benefit many of the crops that are heavily relying on the pollination, for instance. Wider benefits is not just food security and nutrition, health and well-being, and livelihood. And so some of the effects have not just mitigating negative climate impacts, they have positive co-benefits. But we see this adaptation has increased, but it's not even, and it's not taking place everywhere, and it's not fast enough. Other concerns are that adaptation doesn't solve all the problems and climate change. There are apparently limits to adaptation. Even effective adaptation will not work as global change proceeds. We're particularly concerned about the food security issue will be much, much worse above 2 degrees, where adaptation really, soft adaptation will be reached at that global temperature level. Maladaptation is another concern that results in unintended consequences. And so the most disadvantaged groups are most affected. So even though the adaptation works in some groups and some areas, and that may not be work, that may have negative impact in some regions. For instance, was large-scale groundwater-dependent irrigation, and that can benefit some of the large-scale, well-equipped farming systems, but that can deplete water resources for the local farmers. And those are one major concerns about this adaptation, unintended consequences. Financial constraints are still exist, and both mitigation and adaptation do not receive enough financial assistance. Uh, the new effective adaptation do not spread voluntarily, and they need support from institutionally and financially. But these are still lacking. The way we have to look at the adaptation and mitigation at the same time is like this. This is the new understanding from my new IPCC report. Climate change is affecting human system and ecosystem, but they are heavily interrelated, intertwined. How we respond to climate change will affect ecosystems, and impacts of ecosystems in turn affect our responses to climate change. So the solutions need to be very multidimensional. We have to think not just looking at mitigation of the climate change impacts, but we need to look at biodiversity importance. That in turn will benefit our society. So that's a difficult solution, but we are now aware of this large concept showing multiple and intertwined relationship. So the brief summary of the whole report of our working group 2 is the science is clear that the climate change is a threat to human well-being and the health of the planet. Any further delay in concerted global action will miss the brief and rapidly closing window to secure a livable future. And while we hope that this report proposes the solutions to this world. Looking at food systems, we are seeing a large negative impact on climate change, but at the same time, the food system themselves provide some of the negative impacts on climate change. And as you can see here, food system as a whole and produce greenhouse gas and about 30% of the human-induced greenhouse gas. And that ranges from agriculture, land use, and beyond the farm gate that includes society. And that's the industry and retailing. We're just looking at this agriculture side in this presentation, and particularly with regard to Asia. This is the greenhouse gas emission map from cropland, and reddish color showing the greater emission of the greenhouse gas. And as you can see clearly, that red spots are distributed heavily, almost concentrated heavily in Asia. That's largely based on rice methane emission. And rice is important crops, but at the same time produces lots of methane. So it's our task to reduce much of the greenhouse gas emission from the atmosphere. So that's one of the reasons why we are working heavily on how we can mitigate this greenhouse gas as the means of mitigating climate change. So these are some of the findings, the key findings from IPCC. I'll now like to turn to what NARO has been doing to mitigate this climate change impact and on climate change itself. Can we have a quick look at our institute presentation of a video showing our framework of the work, please. Okay, thank you very much. So this is a NARO, and as you can see, we work on many different issues related to food and agriculture and climate change. One of the major issues we're working on climate in NARO. So looking at climate change mitigation measures in working in NARO, we are targeting in three major greenhouse gases: carbon dioxide, methane, nitrous oxide. And while looking at CO2 by way of CO soil carbon sequestration, methane mainly from rice paddies, and nitrous oxide from nitrogen fertilizer organic matter. So we keep many. These are all very important greenhouse gas, as we mentioned in the earlier slides. And here are how we measure it and three different gases at the same time. So that's our invention of the equipment that can measure these three different greenhouse gases from the cropland. The first is about CO2, around soil carbon sequestration, climate change mitigation. We know soil is a large sink of carbon, very large sink compared to the atmosphere. And if we can store carbon in soil, and that reduces a burden on atmospheric carbon dioxide. So that's our major target and huge potential there, but we need to keep monitoring how we manage soil, and that results in carbon in the soil. And there's one food per meal initiative for soil that aims to enhance soil carbon sequestration. It's a very ambitious target. And so the way we do it is this, as you can see in this figure, as we apply organic matter in the soil, and soil carbon will increase. And whereas if you do this poor management in the soil, and carbon will lost from the soil. And so that's the important thing is how much. So we use this Ross C model developed in UK and trying to adapt that to our field conditions in Japan. So what we needed to do is we needed to tailor this Ross C model to Japanese soils, and because they're very different from the European soils where these Ross C models are developed. And looking at this upland conditions in the normal soil, original Ross C model was fairly well performing and to reproduce the carbon in the soil. But if you look at the paddy field, and that there was a strong need to modify the Ross C models, particularly for the anaerobic conditions. There's another typical soil type that's in Japan, that's andosol and the volcanic soils, and we need to modify the soil model substantially. But we did it and we succeeded in this modification, and that's now used for the national inventory report and also the nationally determined contribution from the cropland. And this Ross C model is now embedded in one site, web-based decision support to visualizing soil carbon and greenhouse gas emissions. And so the very simple assumptions, we can look at how much carbon we can store in the soil. And depending on the soil type and temperature and precipitation and your management of the crops and soils. And this will be really a basis of what we can do to mitigate this climate change via better soil management. Greenhouse gas emission from the paddy field is through water management is a major study field. Methane is produced in the field under anaerobic conditions. If you submerge water, if you have flooding water, and soil gets reduced, and then carbon decomposed from the organic matter turns into methane instead of carbon dioxide. But carbon dioxide, methane has much greater greenhouse gas effects. So we need to reduce this methane emission substantially. By withdrawing water in mid-seasons, that will substantially reduce the methane emission. And prolonging this mid-season drainage of just 1 week from the conventional one can reduce the methane emissions substantially. Now we are trying to disseminate this water management through Japanese rice farmers. And in Asia, many countries use alternate wet and drying. This also has potential impacts on the reduction of methane emission. And this has been done in many Asian countries, and some successful measurement reduction, likewise 30% reduction has been observed in some countries. So this is this has been done with the Global Research Alliance, and also another successful way of reducing methane emission in Asian countries. Looking at the climate services, we use agro-meteorological grid square data, AMGSD, to understand what the past and future climate look like. This the observation of data is stored in 1 kilometer grid cells across all Japan. And the data has been stored since 1980s and to present. And we also have forecast values and along with some normal year values. So we can have some continuous data sets from the past to the future. And many major elements are stored, and they can be downloaded through the spreadsheet like Excel. And also you can use programming language such as Python to derive these data, and you can use it freely for different purposes. Some of the application examples in NARO have developed include predictions of key crop growth stages, a recommendation fertilizer application, forecasting of disease occurrence, and estimation of soil moisture, and early warning of extreme temperature causing cool or heat damages. And these can be used for the early warning climate services to do these, to try to avoid these negative impacts. And we have also developed the application for water management using a smartphone and by automated irrigation system that regulates water level and trying to minimize the negative impacts of methane emission and also keep rice healthy during the course of growing season. And what's one point we would like to emphasize that these scientific-based climate actions need really good data. Fortunately, we have long-term soil data that can test raw sea models, carbon models. We have also a nice digital soil map that allows us to do some calculation of carbon storage capacity in the soil across Japan. We have automated meteorological observation network along the Japan, about 1,300 locations throughout Japan. These are the fundamentals of the data that's supporting our system. In conclusion, from these slides, we need actually apparently urgent actions needed on climate change to adapt to avoid growing losses and damages. And solutions have to be account for the differences in vulnerability and across climate and biodiversity in human societies. And reductions and rapid and substantial reductions in greenhouse gas emissions are crucial, and these to keep this adaptation option open. And food systems are responsible for about 30% of greenhouse gas emissions, and we need this reduction badly. and data-driven estimates of mitigation adaptation measures are critical to advancing climate action. I hope this narrow technology can help the implementing this climate change actions in different parts of the world, particularly Asia. Well, we hope this as a COE of Apple, APO, we are determined to contribute to share our knowledge with you. And we are looking forward to working with you and hope we have a good results in the years to come. Thank you very much for your kind attention.
Thank you, Dr. Hasegawa. It was really striking and inspiring to learn about the recent situation in Asian agriculture regarding climate change and the groundbreaking innovations in climate smart agriculture initiated by NARO. So we hope that our audience will be inspired and benefit from your sharing. And now let me start the Q&A session for more in-depth understanding of the topic. So you talked about the dark side and bright sides and problems and solutions of the challenges we are facing today, especially this year. We are all experiencing this heat stress everywhere in the world. So despite the solutions, what do you think some of the potential barriers in implementing those actions, climate actions in the Asian agricultural sector? And how can we overcome these obstacles?
Thank you very much for the question. That are very relevant in many parts of the world, not just Asia. As we introduced, some of the technologies are available and potentially effective, but implementation has still many barriers. That's one of the barriers could be technical issues, and this old technology can be available anywhere in the world. So one size perhaps doesn't fit all. So we need to have very tailored technology in different places, and that needs some of the science and collaboration with local people. The other one is the incentive for practitioners, and are we really benefiting from these implementation? We know that this works for some aspects of the climate change, and but is that really good for practitioners? And we need to have some of the really common understanding. If if the technology works for many different aspects, many different co-benefits, we can convince. But if the yield benefits is low, even negative, and those are the ones that really farmers have have hard adapting. So we need to have multiple views, and just not just this simple solution can be there. Uh, uh, I think what's important is that we need financial institutional support to spread these multiple benefits to realize, and that needs some of the capacity building, education, and institutional help. I think without those common understanding, shared understanding by the society, these implementation will be difficult. So that's I think that's one of the major barriers, obstacles. But I think we can be clever to do some of the work to reducing those barriers in the future. Thank
Thank you
you.
so much. Yes, you stress very important things about tailor-made solutions because the awareness and the opportunities are not same level everywhere. So thank you very much for your insight. So you provided some examples from NARO, successful climate action initiatives. And actually, I had the chance to visit NARO premises, and I was really astonished by the innovative solutions. And it was my first time to see a paddy field also, because in my country we have more like wheat crops. And so, thank you very much. And no wonder Japan is one of the leading countries in studies on rice. So, but I also wonder, can you provide some other examples of these kind of initiatives and projects in Asia that have resulted in positive outcomes? And what made them successful, actually?
Thank you very much. I think perhaps the audience knows better than myself about this local practitioner, successful practices or initiatives and climate actions in Asia. But there are some common aspects of the potential effective solutions. One is that we have, as I said, we need to have some diverse solutions. Diversification, not just looking at single system, is a key to succeed. That can convey multiple options. Again, we have some barriers to implement those, but I think diversification is one issue. And the other one is about readiness of the implementing the systems. And I introduced some of the example like alternate western drying in Asia. Some countries have see the potential of reduction of methane emission, for instance. But so far, some of the Japanese colleagues have studied uptake of AWD, alternate western drying. A successful example relies on the somehow basic infrastructure, whether the water management can be readily made. And also, importantly, this water management, alternative water management, can give the farmers benefits like a potential yield increase due to this system. So the important key to the success is not just one single fact, but we need to look at multiple benefits, and that can be conveyed from this system. So again, that's what's important is that we need to measure those different aspects or different benefits and trade-offs, and that can be brought about these different new technologies. And we just need to convince the growers and practitioners we have making life different. So these are the messages, scientifically based messages that can be useful for implementing or uptake for the new technology. Thank you.
Thank you again for your answer. So, Dr. Hasegawa, I'm also wondering, the one of the biggest actors actually are smallholder farmers. And for example, I was very astonished by reading Masanobu Fukuoka in Japan. He was a pioneer in natural agriculture. So he wrote a book about straw bale revolution. So he found his own techniques to deal with straw bale, and maybe also he worked on climate change effects. So, what can smallholder farmers have the potential? They lack resources and access to information, but how can they be involved in climate action initiatives to benefit from these practices?
Thank you for the question. And there's actually a growing awareness of how small farmers are important in food security, and not just for themselves as farmers, but for the whole global community. And this the unfortunately ability to access latest technology, newest technologies are still limited for smallholders. But I think the greatest, well, we could say advantage of the smallholders is that they can do a little more elaborate caring or practices in their field. Apart from this large scale farming where there is fine-tuned practices is sometimes difficult, and diversification is often easily done by smallholders. They can look at their individual field very carefully. So those are the potential advantage that smallholder farmers can do. But again, as you pointed very correctly, the access to information and technologies is still limited, and that's somehow we solved. And last thing we'd like to see is that new technology creates bigger differences between large farmers and small farmers. And technology, the information should be equal equally accessed or equity is a major issue about climate information. And so in that sense, fine-tuned information that can be available easily for farmers is the key. So I think the basic infrastructure for data is there, but the dissemination of the flow of information, we need to work a lot on that. But with that, we have some potentials for the small holders that they can manage land more elaborately than the large-scale farming. I think that's a great potential there. Thank you.
Thank you very much for your clarification. And my next question, Dr. Hasegawa, you explained about International Panel on Climate Change, the scenarios and the scientific research, but how do you think international cooperation further play a role in sharing this knowledge and best practices about climate resilience?
Thank you very much. Again, this climate and environmental issues are actually borderless, and so we should not. It's the information is much better valued if you have broader aspect of information. If you are living in one country, but it's important to show or see shared information from the adjacent countries and also some of the larger scale countries. And so the climate information services should be somehow scale free. I mean, it has to be everywhere and people can access. And international cooperation plays a major role in sharing that information. And that's one. The second part is the technology, and that's also another issue. And the climate change is created by human, mostly in developed countries, and but those who are suffering from climate change is mostly in developing countries. So this actually already taking inequity has to be solved by sharing different technology from different world and sharing reduce the minimum impact to have better peaceful world. And so to do that, this technology and scientific understanding have to be shared in the local context, and that's important. And communication throughout across the different countries will be a really important asset to implement or proceed climate actions. Thank you.
Thank you so much. So let me connect this with my last question. As we mentioned, and NARO is the new host for the 5th Center of Excellence on climate smart agriculture to share all these experience and best practices in Asia Pacific. And so through which activities will these COE share these practices in Asia? Can you briefly explain?
Thank you. First of all, thank you for selecting NARO as the COE, and we are really delighted to have this opportunity to work with you. And we are hopefully working very closely together with many NPOs to share our knowledge across different countries. Importantly, our knowledge, our technology is not universal. This is a fundamental aspect of technology. We need to, again, tailor this technology in different places and different climates. And we are also, we are of course sharing our technology, but important thing is that we are also learning what is happening in the different places. And by sharing those ideas, basic data, and some of the tools, and we can connect. And hopefully through our collaboration with some symposium or mutual talk, and also the capacity building of the NPOs, and we hopefully share our knowledge and tailor to each country. And hopefully that was helpful for NDCs and further beyond 2030 climate actions. Thank you.
Thank you, Dr. Hasegawa. We're also looking forward to work in these pilot projects and studies together. And we thank you again for your many useful insights. Would you like to share any final remarks with our viewers?
Thank you very much. Perhaps I reiterate this issue. We are not just to distribute our technology alone. It's not just our task. I think it's a collaboration and sharing and learning is all processes together. I think that's the most important part of the scientific technology dissemination. And in that sense, I'm really looking forward to working with you. Thank you very much.
Thank you once again, Professor, for joining us. And I'm sure that our viewers really enjoyed and definitely got inspired from your presentation.
Thank
So
you very
before
much.
closing our P-Talk, yes, I would like to thank our viewers once again. And if they have questions, they can leave in the chat box so we can answer later. So see you in the next P-Talk. Goodbye.